Let's understand convolution codes, which is a special case of cyclic codes with multiple error correcting capability. For convolutional codes, the encoder circuit diagram will be given in the problem statement. If you remember the encoder circuit diagram of cyclic codes, which consisted of flip-flops forming a shift register, you will find the same kind of diagram is shown in the figure here. It consists of two flip-flops S1 and S2 and two XOR gates or modulo 2 adders. Input is applied to flip-flop S1 and output of flip-flop S1 is given to flip-flop S2. The upper modulo 2 adder gets its inputs from S1 from input and S2, and the output of upper modulo 2 adder is noted as the output V1. The lower modulo 2 adder gets its inputs from three sides: the input signal, output of flip-flop S1 and output of flip-flop S2. Output of lower modulo 2 adder is denoted by output V2. Before solving the numerical, let's understand the problem statement. For convolutional encoder shown in figure, draw the state and release diagram. Decode the sequence 01000100 using Viterbi algorithm and comment on number of errors corrected. So this problem statement consists of four parts. Firstly, we need to draw the state diagram, then the release diagram. Then we should apply Viterbi algorithm to decode the sequence given. And finally, we have to comment on the number of errors corrected. Let's start with the solution. To draw the state diagram, we first need to draw the state table. Let's understand how to draw the state table. State table consists of the previous states and current states of the flip-flops S1 and S2. So, we'll write the column of previous state, for S1 and S2. Next column will give us the next state for S1 and S2. Last columns are for outputs, which are denoted by V1 and V2. Outputs will depend upon the previous states and the input message applied. Right? Now, since there are two flip-flops, we have 2 raised to 2, that is 4 combinations for the states. So, the previous states will have 4 combinations: 0, 0, 0, 1, 1, 0 and 1, 1. In every state, we can apply the input, and there are 2 possibilities of input, that is 0 or 1. So, the input can be 0 or it can be 1. Again, we can apply input equal to 1 in state 0, 0. For the next state 0, 1, 2 possibilities of input 0 and 1. So, again we repeat the state 0, 1. In the third state, there are 2 possibilities of input 0 and 1. So, 2 possibilities of previous states 1, 0 with input 0. Same state 1, 0 can have input equal to 1. The last state 1, 1 can have input equal to 0, and the next combination is the state 1, 1 can have input equal to 1. Now, as we had seen in case of cyclic codes, whenever an input bit shifts in or gets applied, it shifts into flip-flop S1, and bit into flip-flop S1 shifts into flip-flop S2, and the bit in the flip-flop S2 gets applied to the modulo 2 adders, and accordingly the output V1 and V2 will get changed. So we can see that in the next state S1 is equal to M and S2 is equal to S1, right? So for writing the next state, we just have to simply copy the columns M and S1 below S1 and S2 in the next state. So we'll get the next states as 0, 1, 0, 1, 0, 1, 0, 1 and column of S1 as it is 4 times 0 and 4 times 1. Now how to write the values of V1 and V2? Obviously, we need to write the equations for V1 and V2. From the circuit diagram, we can see V1 is equal to V1 is the output of upper modulo 2 adder which has its inputs from input M and output of S2. So we can write V1 is equal to M XOR S2. Similarly, V2 is the output of lower modulo 2 adder which gets its inputs from input M, output of flip-flop S1 and output of flip-flop S2. So V2 is equal to M XOR S1 XOR S2, right? So by applying these equations for V1 and V2 and considering the value of M and previous states of S1 and S2, not the next state, we have to consider previous states of S1 and S2 to find out the values of V1 and V2. So accordingly, we can do the calculations. V1 is equal to M XOR S2. So M is 0, previous state S2 is 0, 0 XOR 0 is 0. Similarly for V2, the equation is M XOR S1 XOR S2. So here we have the three inputs as 0, 0, 0. Hence the XORing output comes out to be 0. Similarly, we'll go for the next state. The value of M is 1, S2 is 0. So the value of V1 is 1 and V2 is 1 XOR 0, 1. 1 XOR 0, 1. So we get V1 and V2 as 1, 1. In the similar fashion, we'll write down the outputs V1 and V2 for all the states. And this completes your state table. So state table is necessary to draw the state diagram. So let's understand how to draw the state diagram. We have 4 states. We'll write state A as 0, 0, state B as 0, 1, state C as 1, 0 and state D as 1, 1. I hope you must have studied how to draw the state diagrams in your DLD syllabus or digital electronics syllabus. We'll draw the states here. This is state A, 0, 0. This is state B, 0, 1. Here we draw state C, which is 1, 0. And lastly, state D, which is 1, 1. Now let's make use of state table. When you are in state 0 0. An input is 0, next state is 0 0 while output is 0 0. So this is shown in this way. You are in state A 0 0, and if input is 0, you remain in same state 0 0 with output equal to 0 0. Next, again you are in state 0 0, but now the input is 1. The next state is 1 0 and the output is 1 1. So this is denoted as, from state 0 0 you move to state 1 1. So from A we move to state 1 0, and here the output is equal to 1 1, which is written on the dashed arrow. Remember, when the input is 0, we indicate the state change by solid line, and when the input is 1, we indicate the state change